The machine most of us recognize today, whether it's a laptop, a desktop sitting under a desk, or the tablet in your hands, is the personal computer. It serves as our universal standard for everyday digital tasks. In the past, machines capable of doing those tasks were massive. That changed when an entire system could be built around a single microprocessor chip. By shrinking the central processing unit down to a microscopic scale, computers became small enough to sit on a desk instead of filling an entire room. No matter the brand or shape, every one of these machines shares the same core hardware. They all rely on a motherboard to connect a CPU, RAM for short-term memory, and a drive for long-term storage. But the personal in personal computer highlights its main limitation. This setup is designed specifically to handle a wide variety of tasks, but only for exactly one person at a time. This architecture is complete. Yet the physical size of these machines ranges from a single chip inside a smartwatch all the way up to sprawling server racks that take up an entire floor. To understand why that scale varies, we start at the absolute bottom of the ladder. Embedded computers take those standard PC components, the processor, the memory, everything, and shrink them down to fit onto a single tiny piece of silicon. These tiny chips sacrifice the power to browse the web or run video games. Instead, they are built to execute exactly one specific repetitive job. An automated teller machine is run by an embedded system. The computer inside is engineered solely to read your bank card, confirm your PIN, and dispense your cash. You interact with this single task logic constantly. It's the system inside a smartwatch tracking your heart rate, or the chip inside a smart TV engineered to launch streaming apps. Limiting these systems to a single job makes them incredibly cheap to manufacture. That affordability is what allows companies to mass produce them and embed them into almost every electronic device we own. Stepping up from individual devices, the demands change. When universities or hospitals need a system that can support hundreds to thousands of users at the exact same time, they rely on a mid-range computer, or mini computer. This chart shows the hardware gap between a PC and a server. A PC maxes out at 16 gigabytes of RAM and one processor, while a mini computer utilizes multiple processors and 128 gigabytes. Furthermore, while desktops sleep daily, servers run databases requiring 24/7 uptime. Scale that up to a national or global level and you reach the mainframe. These are massive physical installations built to handle the weight of entire global organizations. When a bank needs to process millions of transactions every single second, or an airline is managing worldwide flight schedules in real time, they are relying on mainframe architecture. To maintain that kind of load, modern mainframes pack thousands of CPUs, up to 40 terabytes of RAM, and multiple petabytes of storage. Hardware at this level is engineered for the crowd. It manages millions of simultaneous connections and massive data streams while maintaining absolute reliability. Finally, we arrive at the supercomputer. This is the largest and most powerful machine in existence. Its architecture prioritizes pure mathematical speed and heavy-duty calculations. Scientists use them to churn through data beamed back from space telescopes, and energy companies use them to run complex 3D models of underground geology to locate oil reserves. The engine driving these colossal workloads is an array of thousands of processors, all synchronized to attack the same mathematical problem in parallel. Running thousands of processors at maximum capacity creates a severe physical consequence: extreme heat. Left unchecked, the thermal output of these calculations would rapidly melt standard hardware. To keep these machines functioning, engineers install industrial cooling solutions directly into the facilities, routing chilled water pipes beneath the floorboards to constantly draw heat away from the silicon. Building and cooling a machine of this scale is so expensive and complex that it can only be done by highly funded organizations like NASA or international research centers. This diagram illustrates the full silicon ladder we've just climbed, from the tiny embedded specialist chip up to the personal computer, the multi-user server, and finally the towering calculator at the top. Across every single tier, you will find the same core architecture: a central processing unit, memory to hold the data, and storage to keep it long-term. Now that you know how computer sizes scale, it's time to see how this hardware evolved over time. Click here to watch my video breaking down every generation of computer history.